One of the greatest things about science is being able to ask these questions that people through the millennia have wondered about. Like, why does the wind blow? Well, if we pull up a typical weatherman's map, we'll see a bunch of H's and L's. That stands for high and low pressure. And just like if you try to make high pressure in your mouth, right? If you open those lips just a little bit, wind comes out. It goes from a high pressure area to a low pressure area. I would bet right here wind is blowing this way. The high and lows result from uneven heating of the Earth's surface. That's very important. So ultimately, the source of wind energy is the sun, because the sun, which of course is powered by nuclear fusion, ultimately heats different parts of the Earth, and therefore the pressure goes up, all the hot air rises, pressure is lower somewhere else, wind blows from high to low. But that's not the whole story. You see, if you were driving down the road and you stuck your hand out of the window, you would feel wind. Our whole planet is effectively driving down the road because it's rotating. If I looked at the North Pole, right, and now here's our planet. The planet is turning around. In fact, so fast that one given spot only takes 24 hours for it to absolutely turn all the way around. So, looking down at the North Pole, Earth is rotating this way. You're sitting here out in central Illinois, right? And you, here you are, right? And you stick your hand out and you feel the wind rushing by, because even though the Earth is turning, right, the air that's stuck to the Earth, right here, it's going to be moving right along with it, but it kind of lags behind. After all, there's not a whole lot of friction between air and the Earth. So if you're doing that, and you're moving this way, and you put your hand out the window, you're going to feel this wind blowing your hair, streaming behind you. Only this picture isn't quite right. At least in North America, Europe, in this sort of northern part of the latitudes where a large population, China, is across the world. Because this right here in America, well, this would be New York, right? And this would be Los Angeles. And the wind doesn't blow from the east to the west. Generally, in the United States, the wind blows the opposite direction. So what's going on? Let's first not take the top view, but let's take a side view. Let's imagine right here that the Earth was a cylinder. Okay, that's great. And the Earth is turning this way. There's the axis of the cylinder. This is sort of like looking down on the top. And indeed, if it was going this way, that means the motion of the cylinder is this way, the wind would be conveniently coming across here from east to west. And this would be fine, and it would work if the Earth was a cylinder, because all of this wind would conveniently wrap right around. It would all stay next to each other. It wouldn't make any voids. And we'd have a uniform wind going past our Earth. The problem is that our Earth is not a cylinder, right? The Earth is a sphere. And indeed, here's the North Pole, the axis, it is still rotating. But if I looked at that same picture, this wind on the equator, no problem. In fact, the wind on the equator does go from east to west. But if I went up a little bit further, right, this wind has smaller distance to go around. If you think about it, up here on the North Pole, if you were standing perfectly there and could somehow be observed from space, the Earth wouldn't be rotating very much at all. On the equator, you're going really, really fast. So all of this air has to stay together. It has to actually form a continuous blanket. So even though you have this strong circulation right here at the equator, because up here this circulation has to be very, very slow and weak at the two poles, there have to be regions in between where you have counterflow. And this region up here in the northern hemisphere that has the counterflow happens to hit almost all the major population areas across the planet. Well, because the continents are mostly in the north. You're going to hit China, you're going to hit North America, you're going to hit Europe. And our wind goes the opposite direction that you might think just because the Earth is rotating. Here's an actual picture of what the wind would look like going around a sphere. As you can see on the equator, the direction of spin, or opposite to the direction of spin, since the wind isn't connected to the Earth as well. Up on the very tops, it still goes that same way, but in between, it's got to go the other way. And then between the two places, there has to be basically no winds at all. Horse latitudes, right, where there's a difference between the two flow directions. If we actually put the continents back on, you can see that you get here in North America this nice west to east flow. Well, this works great, but keep in mind that the whole Earth isn't covered in uniform land. It would look like this. We also have water to contend with. And when we have water to contend with, the water doesn't change in temperature near as dramatically as the air does in any one given spot. You know that, right? It's always cooler by the lake or warmer by the lake, depending if you're in the winter or summer. So when we actually put that all together, things get a little more complicated. But generally, in the middle of the equator, wind goes that way. And up or down in latitude from that, it goes the opposite direction. So that's why the wind blows. But when we're trying to talk about wind power, what we want to know is not just which direction it blows. In fact, with the rotating windmills that can always face into the wind, it may not matter all that much. What we want to know is how fast does it go. Because remember, the power you get from a windmill goes as the speed cubed. And the speed cubed is a huge effect. Let's look at a wind map of the United States. So the colors on this map go from sort of a light green here, that's 4 meters per second, to the actual bright blue, which you only see in a few locations, and that's around 10 or 10.5 meters per second. You might say, oh, some, factor of 2 in wind from maybe 5 to 10. Does that really make a difference? Well, let's look at it. What's 5 cubed compared to 10 cubed? This is 1,000. 5 cubed is 125. We might only be doubling the wind speed, but the power has gone up times 8. So clearly you're going to put your windmills in the highest possible winds you can. So where is it bright blue? Right over here in Altamont Pass, just inside San Francisco Bay. Best spot in the country on land for wind. Notice offshore is always a little windier than onshore. Too bad you have to build the turbine out in the water, which makes it a little tougher. But you can also see some formations, like why is the wind always blowing across the plains? Well, remember, right here are the Rocky Mountains. You come over the mountains, the air expands, it comes back down to the plains, nothing's in the way. Wonderful wind resource. And then there's another interesting phenomena. You can see where this red band kind of cuts across central Illinois. Let's zoom in on that. Since I'm taping this right now here in Champaign, Illinois, and if you look just north of us along the highways, you'll see, giant wind farms. This ridge right here, this slight ridge, not something you could really tell at all by looking out the window. Oh, we're at higher elevation. Slight ridge. As you go above the Earth's surface, the wind gets faster and faster because, of course, it's not as connected to the ground. So even a slight rise gives you a slight increase in wind velocity and therefore a better place to put windmills. This slight rise was caused because when the Great Lakes were carved out by glaciers, this is where it ended. And the moraines, the slight amount of material built up there, that was the edge of the glacial formation, is deposited in a very broad low ridge, leading to wind farms being in these red locations. That's what you need to know about why the wind blows and why it's so important.